Hello and welcome to this quick look at a blood buffer leveled response 6-mark exam question. This is a common application of buffer ratios that comes up quite a bit in A-level chemistry. It's also quite interesting because it's obviously got a sort of medical / physiological component to it as well. So before starting, I'm going to do a quick review of the buffer ratio calculation, just in case you haven't had a go at it recently. So the question will normally give you two things: the pH the buffer is required to maintain, and the Ka of the weak acid the buffer is made from. So the first thing to do is to use the pH value to work out the hydrogen ion concentration, or H plus aqueous in square brackets, as it's written here, by doing 10 to the minus pH. And then you write out the Ka expression and insert the Ka value provided. Then you'll have two things that you already know. So you'll have a calculation that looks something like this. This is your Ka expression. Obviously, if you have the specifics of a particular buffer and the identity of the weak acid, you wouldn't put A minus and HA. You'd put the actual conjugate base ion in the salt in the numerator up there, and down at the bottom you'd put the full formula of the weak acid. So what this means is that the parts of that Ka expression that are in pink will already be known. They'll have values attached to them at this point. So what we're trying to find is the ratio of the weak acid concentration in its undissociated form to the conjugate base that weak acid is attached to. So by rearranging it, what happens is by dividing Ka by H plus, you get the A minus over HA ratio, which is essentially what you're looking for. So let's have a go. Let's have a look at a question. This is a 6 marker. You can tell that because it's got the little asterisk at the top. So where it tells you explain in terms of equilibrium how the carbonic acid hydrogen carbonate mixture acts as a buffer in the control of blood pH, that's one strand of the answer. But I'm going to start with the calculate the HCO3 minus to H2CO3 ratio, because that's what we've just spent a little bit of time looking at. So the first thing to do, like we talked about, was to go for 10 to the minus pH. Now you'll notice I'm leaving the calculator value in there. You don't have to write this out. You could write 3.98 ... for example, and save it to your calculator's memory. Now the next piece of information is given to us as a pK value. There's a simple conversion you can do. So Ka is 10 to the minus pKa. So the similar type of calculation that we did a moment ago, and this time it gets us 4.168693835 times 10 to the minus 7. Both of those are expressed as moles per decimeter to the minus 3. So now we write out the Ka expression, and we do the rearrangement like we did before, and we put in the numbers. So running our numbers through our calculator gives us 10.47. So that means that the HCO3 minus ratio is 10.47 times more concentrated. Sorry, the concentration of HCO3 minus is 10 times more than the concentration of H2CO3 in healthy blood. But you can just write it as 10.47 and express it like this, and they'll be fine. So if we put all that to the side and now come back and revisit the second part, and this part is explaining in terms of equilibrium how the carbonic acid hydrogen carbonate mixture acts as a buffer in the control of blood pH. So we're given the formulae for the species that are involved. So the first thing to do is to write out the weak acid dissociation using the formula we're given. So like I said before, you don't use HA or A minus here, you just use the actual weak acid that's of interest. So in this case it's carbonic acid. So the first thing to do, in no particular order, is to say what happens when either acid or alkali is added. I'm going to start with what happens when the acid is added. So the two things to say are the reaction that takes place. So the incoming H plus reacts with the conjugate base ion there, the hydrogen carbonate ion, and that gives you carbonic acid. So essentially it's this reaction in reverse, isn't it? So you can write in a a normal arrow. It doesn't have to be an equilibrium arrow this time, because that is the reaction that will take place. But the position of equilibrium in that dissociation will shift to the left. And with the alkali, what happens is the OH minus will react with the dissociated H plus, and therefore drive the equilibrium to the right. So what's happening here is that H plus that I'm hovering over at the moment is removed and it's turned into water. As its concentration drops, Le Chatelier's principle would suggest that the position of equilibrium will shift to the right to replace it. So that's all you really need to say. You don't need to go into the fact that H2CO3 will dissociate further, because just saying the position of equilibrium shifts to the right will cover you for that. Okay, I hope this has been a useful look at not only what happens in the blood in terms of buffers, but how we could answer a 6-mark question where it's often got 2 separate strands to the instructions. Okay, as always, thanks for listening. Until next time, see you soon.